Hey fellow problem solvers, Colfax Math here. You can't learn how to juggle by watching the video. The only way you learn how to juggle is practice. The only way you learn how to do well on a standardized math test is to practice as well. I wrote this book right here, Math Test Success, ASVAB Algebra, to give you the opportunity to do a lot of practice so you could be as successful as possible on any standardized math test. 25 chapters in this book. I have a video for every chapter, but now I'm doing a series of 5 videos to condense a lot more of it into 5 single videos. The book is split into 5 parts, 25 chapters. Today's video is part 3, advanced algebra topics. So in today's video, I'm going to go over systems of linear equations. We're going to go from x to x and y. We're going to look at exponents and radicals, polynomials, quadratic equations, functions, graphs, and coordinate geometry. There's a ton here. It's going to be a long video. Get the book on Amazon, follow along in the book, or if you don't have the book, get a notebook and paper and pencil out, take notes. The act of writing stuff down helps you to remember it. Pause the video, do the practice problems, unpause the video, see how you did. All right, let's get started with Chapter 10, Systems of Linear Equations. Remember, this all started with the number line, and I kept saying how essential this is. This is your x number line, center of it 0, 1, 2, negative values over here. And then we took between 0 and 1, and we split that into parts and pieces. We looked at those parts and pieces as fractions, decimals, percents, but it's all on this number line. Now we're looking at equations with 2 variables, x and y. All we're doing is we're going from one-dimensional space of a line, adding a second dimension to it, and calling it y. So I could graph in one-dimensional space, x is equal to 2. That's the dot right there. And inequality, x is less than 2. Open circle that way. And now we're not talking about the value of x. We're talking about an ordered pair, x, y. There are 2 variables, not just one. This is always over, and this is always up. You can think of it as you walk into a building, you got to walk over to the elevator, and then you go up the elevator. So x is always over, y is always up. This is called the Cartesian coordinate system. This is quadrant 1, 2, 3, and 4. And first thing we do is we go from one-dimensional space to two-dimensional space. Stay positive in quadrant 1. We rotate counterclockwise to add in our negative values. Because we could be negative in x and negative in y, it doesn't double, it quadruples. Okay, so if I had an ordered pair like 1, 2, always over first, I go over 1, and then I go up 2. And then there's my ordered pair or my coordinate. Chapter 15 is specifically more about Cartesian coordinates. I'm going to talk more about them. But know now that we are solving a system with 2 variables. Therefore, we have to have 2 equations. Okay, so the way to do this, there's a lot of ways to solve. The first one we're going to look at is substitution. So I have 2 variables, therefore I have to have 2 equations. I know that y is equal to this right here, and then I have another equation. If y is equal to that, I could substitute that y value in right here. Just like in algebra, where we were evaluating expressions with variables in them, we were giving you a value for that variable and you plug it in. Now that's the exact same thing. We're giving you a value for that variable and we're going to plug it in. The key is that now it's a variable in that variable. Okay, so what I'm saying is y equals that. I plug it in there. I have that 3x. So in blue right here, I still have that 3x plus y is equal to 6. And then I know y is 2x plus 1. So I have gone from one equation with 2 variables, combining it with the second one through substitution, and now I have one equation with 1 variable. I solved that just like we did in the previous video in part 2. 3x and 2x is 5x. I subtract 1 from both sides. 5x is equal to 5. divide both sides by 5. You remember isolating the variable x. X is by itself. 5 divided by 5 is equal to 1. I have that value for 1. That is half my answer. Remember, I'm looking for an ordered pair, x and y. So I have that value for x. I take it, I plug it back into either equation, doesn't really matter which one, to find my y value. So 3 times x, well, x is 1, plus y equals 6. 3 plus y equals 6. 3 plus y equals 6. Subtract 3 from both sides, and y is equal to 3. So I'm looking for an ordered pair, an xy value. I solve for x first. X is equal to 1. Y is equal to 3. I have my solution. The check is I should be able to plug it into either equation. It should work. So 3 to be equal to 2 times 1 plus 1 it is. 3 times 1 plus y, 3. 3 plus 3 should equal 6. And it does. So I could see I did that correctly. It's a big leap from the last video to this, where we're going from 1 variable to 2 variables. Okay, let's go ahead and do some of these. Maybe we'll do number 2. Pause the video, give it a try. Here I have a value for a. Take that value for a, plug it in there. There's a key here. I have that 3 out front. Whoops, 3 times a. And I'm telling you a is equal to 2b minus 1. So there's 3a plus b equals 11. And here's a trick right here. You have to distribute that 3 through the whole quantity. Because 3 times a is all of that. So I have to take all of that, multiply it by 3. That gives me 6b minus 3 plus b equals 11. Combining similar terms, 7b minus 3 equals 11. Add 3 to both sides, 7b equals 14. Divide both sides by 2, b is equal to 2. That's not my answer. That's only going to be half my answer. That is my first value. Oh, no, that's b, so I'm going to put it second. I'm going to take that value for b, plug it in there, and a is equal to 2 times b minus 1. So a is equal to 4 minus 1, 3. So my solution is a equals 3, b equals 2. Okay, go ahead and make sure you do all of these problems right here through substitution. And then we'll move on to elimination. I'm going to go ahead and do one word problem here. These word problems are kind of tough. The sum of 2 numbers is 25. I don't know what those numbers are, but it is 2 numbers. So I have x plus y. The sum, adding x plus y, equals 25. One number, we'll say this one number, x. X is 5 more than the other number. Find the 2 numbers using substitution. Well, I have 2 variables, 2 equations. I have that. I have x is equal to this. Take that value of x, I plug it in there. Y plus 5, that's going in there for x. Plus out y equals 25. Y plus y is 2y. Subtract 5 from both sides. 25 minus that 5 is 20. Divide both sides by 2. Y is equal to 10. Again, that's not my answer. It's only half my answer. Find the 2 numbers. So y is 10. I'm going to take that value for y, plug it back into either equation. I'll plug it into there. X plus 10 equals 25. X is equal to 15. My ordered pair, 15y or xy, 15, 10, this is my ordered pair. Let me see if that works. The sum of 2 numbers is 25. Yes, they added 25. One number is 5 more than the other number. Yes, it is. Find the 2 numbers using substitution. Okay, Moving on to section 10.2, solving by elimination. So what you want to do here, this is another way to do the exact same thing. Not better, not worse. Sometimes substitution will work really well. Sometimes elimination will work really well. With enough practice, you'll know which one to use. Almost in all cases, either one will work. Okay, so in elimination, you want to align the equation so the like terms are lined up vertically. Multiply to get them to be equal values. And then you need to add or subtract the two equations to get a variable to drop out. Solve. You're going to only be able to solve for one variable. The whole point of elimination is to combine two linear equations to get rid of one of the variables, solve for the other variable, plug it back in to find both values. And then, as always, check your solution. Okay, so I have this system of equations right here. 2x plus 3y. I can multiply either one to get rid of the other term. But I'm just going to write this one down, the top one in red. 2x plus 3y is equal to 8. Now I'm going to modify the bottom one so that I can align them and have something cancel out. So what I'm going to do with this x minus y equals 1, I think I want to get rid of the x's. I could do it either way, but I'm going to get rid of the x's. It is an equation. I can do whatever I want, as long as I do it to both sides. So I'm going to multiply the left side by a -2 and the right side by a -2. That's going to give me -2x. Negative negative is positive 2y, and that is going to be equal to -2. I did all of that so that I could align the x terms and have them cancel out, because 2x plus -2x is 0. 3y plus 2y is 5y. 8 and -2 is 6. Then y divided both sides by 5 is equal to 6 over 5. Again, that's not my solution. It's only half my solution. If I wanted to, I could have taken the second term, or the second equation, multiplied it by 3 to get 3x minus 3y is equal to 3. And then the y's would have canceled out. Either way would have worked. Substitution would have worked as well. I have that value for y. I take that value for y. I plug it into either equation. I'm going to plug it into that one and solve for x. Let me use a different color now. X minus y is 6/5, is equal to 1. I'm going to add 6/5 to both sides. So x is equal to 1. Well, 1 is 5/5 plus 6/5. The way I add fractions, I have to have that common denominator. So I skip that step, turn that into a fraction with a denominator of 5. Add across the top to get 11. Keep the bottom the same, 5. Value for x, value for y. My solution is an ordered pair, x, y. It's a hard problem. It incorporates, every previous chapter, we're looking at fractions, adding fractions, we're looking at single variables, combining stuff. If you're getting this, it is fantastic. You're moving forward and you're doing great work. If this is still all a little bit, unclear, go back and review those first chapters. All of this stuff is so cumulative based on the previous stuff that you really have to get the previous chapters. Okay, let's do a couple of practice problems here. This one looks like an easy one. Pause the video, give it a try. I say it's easy. I say it's easy because I just have to line this up here, and my y's will cancel. So I have x plus y equals 2. All I've done is rewrote that one. I don't have to multiply it by anything because I can see those y's will cancel. X plus x is 2x. Y, negative y cancels. 12, divide both sides by 2, x is equal to 6. Have that value for x, take it, plug it into either equation. I'll plug it in there. 6 plus y equals 2. Subtract 6, y equals -4. My value, my ordered pair, 6, -4, xy. Okay, I don't want this, we've got a lot of content to cover, so I don't want this to take too long. I'll just pause the video. If you have the book, work your way all the way through that practice test, see if you got it down, keep practicing, unpause the video, watch how I do it. Number 1, solve the system by substitution. I could see y equals this. I'm going to take that and plug it right in there to get 2x plus y. Well, y is 3x minus 1, and that's equal to 9. Combine my similar terms, 5x, add 1 to both sides, 10, divide both sides by 5, x is equal to 2. Again, not my whole solution, only half my solution. I take that value of x, I plug it in right there. Either way, either one. 2 times x plus y equals 9. 4 plus y equals 9. Subtract 4, y is equal to 5. I have a value for x, value for y. My solution is an ordered pair, 2, 5, xy. All right, hopefully we're there. You got all of these down. And then from there, we're going to move on to chapter 11. I think before we do that, I'll do one of these word problems, and then we'll move on to chapter 11. If you need a channel, think about subscribing, become a member, support the channel, buy the book. Okay. This is kind of similar to the last one. Let's see if we could do this one. A movie theater sells tickets for $8 for adults and children. I can call that adult and children. The total of 120 tickets were sold. That means all the adult tickets plus all the children tickets equals 120. The revenue was 780. So this means 8 times the number of adult tickets plus 5 times the number of children tickets is equal to 780. It's a good problem. It's a hard one, but it's a good one. And then now I have 2 equations, 2 variables I need to solve. I could do it a couple of ways. I'm looking at it. I don't know. Linear combinations might be nice. Get rid of that C. Or I could solve for A, get A by itself. I think what I'm going to actually do is I'm going to get rid of that C. So I'm going to multiply both sides by -5. Again, substitution would work just as well. That's going to give me -5a, -5c is equal to -600. Going to combine those two to get 3a. My c's cancel. This is 780 minus 600, 180. Divide both sides by 3. And the number of adult tickets is 180 divided by 3, or 60. Again, not my whole solution. I got to read the problem. How many adult tickets and how many children's tickets were sold? So 60 adult tickets and a total of 120 tickets. I take that 60, plug it in there, subtract 60 from both sides, and I see C is also equal to 60. So let me double check that. 60 plus 60 gives me the 120. 60 times 8, 480, plus 300 gives me 780. So I could see I did that correctly. If you got that one right, fantastic. You're doing great work. Keep at it, and we'll move forward into the next chapter. All right, working on chapter 11 in the book. This is inside of part 3. Today we're going to talk about exponents and radicals. What an exponent is a way to multiply a number by itself. So this right here, let's say I have 5. That is my base. If I want to do 5 times 5, I could say that is 5 to the power of 2. So this is how many times you multiply it by itself. So 5 squared is 25. And then the reverse of that is going to be radicals going backwards. So this is a function, exponential, and then this is a radical to go backwards. We're going to learn the rules of exponents, fractional exponents, going backwards to square roots, how to convert. There's a lot here, so I'll kind of keep the pace going pretty fast. Make sure you've done the previous chapters prior to this one. So some of the rules of exponents is first the product rule of exponents. So the bases have to be the same. So product means to multiply. If I have x squared times x to the third, the bases are the same. I am multiplying. The rule here is you add the exponents together. The quotient rule, again, the bases have to be the same. If I have x to the fourth over x to the first, I subtract the exponents. So I stay with the same base, 4 minus 1, or x to the third. The power rule, if I have x to the third all to the power of 4, I multiply. So this is x to the 12th. The zero exponent rule down here, anything to the 0 power is equal to 1. So 5 to the 0 is equal to 1. So again, let me just recap a couple things. This base right here to the power of is how many times you're going to multiply it together. There are 4 rules we've looked at. The product rule, if these two things are getting multiplied and the bases are the same, you add the exponents. They're getting divided, you subtract the exponents. If the whole thing is to the power of, you multiply them. Anything to the 0 power is equal to 1. The one last rule here is a negative exponent rule. If I have x to the negative 5, I can make that positive by reciprocating it by going 1 over x to the positive 5. And the reverse of that's true too. If I had 1 over x to the negative 2, I can make that negative exponent positive by putting it on the other side. And that would give me x squared. So those are the 5 rules of exponents. And now we're looking at simplifying some examples here. So if this is a problem here, x to the 8th times x squared, I would add the exponents to get x to the 10th. Here I would have x to the 8th. Here I would have to do my parentheses first, use the quotient rule first. Y to the 7 divided by y to the 4th, so I subtract. That would give me y to the 3rd. Y to the 3rd inside the parentheses to the power of 2. Then I would multiply those together to get y to the 6th. Simplifying exponential expressions. Remember, there's no equal sign, so they're just expressions. You're going to see a lot of these in arithmetic reasoning word problems, but more probably in mathematical knowledge where you're just asked to simplify the expression. Here I multiply to get x to the negative 8th. Here I need to make sure everything's to the power of 2. So don't go quickly and go 3x squared. It is 3 squared x squared. 3 squared is 9 to give me 9x squared. Okay, here's a practice test. I'll pause the video and do that. I'll go through some of them, the keys in the book. Okay, number 1, x to the 7th. Number 2, x to the 12th. Number 3, 8, b to the 3rd. 2 times 2 times 2, 8, b to the 3rd. 1 over 9d squared. So this one right here, let me move it up a little bit. This one right here was equal to 3 to the negative 2, d to the negative 2, which is going to be equal to 1 over 3 squared over d squared. Negative exponents, I could just add to get p to the negative 4. So this is p to the negative 4, Or you always leave your answer with a positive exponent, 1 over p to the 4th. N to the negative 9, 1 over n to the 9th. Distributing through the whole quantity here, x to the 8th, x to the 12th. Add my exponents together to get x to the 20th. Okay, let's move up here a little bit. Number 8 or 9. These are starting to get a little harder. Now I'm going to kind of mix in some canceling here. So 3 goes into 3 one time. 3 goes into 27 9 times. So I have a 9 in the bottom. X squared over x to the 1st. I'm going to subtract to get x in the numerator. Y to the 7th over y squared is going to be subtracting y 7 minus 2. This is just equal to a 1. My z to the 3rd, z to the 3rd stays in the denominator. Again, we're just simplifying expressions, combining like terms, canceling, ending with positive exponents there. There's a lot in this chapter. All right, let's start looking at going backwards now. So the reverse of a square is a square root. So if I have the square root of x, that is saying what times itself will equal that. Square root of 36, what times itself will equal 36? So 6 times 6 is 36, but also negative 6 times negative 6 is 36. So there are actually two answers, positive and negative. So what is the square root of 64? That is saying what times itself equals 64, 8 or negative 8. A lot of times you just write the positive down. That's a square root. There's no number written here. It is implied it's a 2. Square meaning 2 side or square area 2. And then now we're going to look at cube roots, where now it's square root, but that's 3. So that is saying what times itself equals 27. So what is the cube root of 27? We'll go backwards and say what times itself is 27. 3 times 3 is 9. 9 times 3, 27. So the cube root of 27 is 3. You could talk about the nth root. That number there could be anything. It could be an integer like 2 or 3, square root, cube root. It could be a million, the millionth root of x. Okay, and they're going to get pretty complex. So let's go ahead and simplify some radicals here. And there are some rules to simplifying these radicals. The first is the product rule. Just like if we did with exponent x to the a times x to the b, we add them. That's the reverse here. So the product rule for radicals or square roots mean the same thing. The square root of ab, you could split that apart to get the square root of a times the square root of b. As an example, the square root of 50 is equal to the square root of 25 times 2. Now that I have that, I can split it apart to get the square root of 25 times the square root of 2. The square root of 25 is an integer 5, so you end with 5 root 2. The quotient rule for radicals, the square root of ab can be split to the square root of a over the square root of b. So if I had the square root of 64 over 9, you might try and divide that first and then get a decimal and be really tricky. But you could split it in the square root of 64 over the square root of 9, leaving you with square root of 64, 8 times 8. So it would be 8. Square root of 9, 3 times 3 is 9, ending with 8/3. Again, a fair bit of these in the arithmetic reasoning portion of the ASVAB. Simplifying radicals with variables. If I have x to the 3rd, I could split that to x squared times x to the 1st, right? I would be adding my exponents to give me x to the 3rd. Square root of a square just makes it on its own. I'll give you another example. If I had the square root of, say, 125 x to the 3rd, I like to break these out if it's to simplify into the factors. And I'm not going to the prime factors just till I get a pair. 25 is a 25 and a 5. 25 is a 5 and a 5. X to the 3rd is an x squared and an x, right? Adding those exponents gives me x to the 3rd. This is the x and the x. Then for every pair, I take one out. So there's a pair of 5s here. I take one out. No pair for this one. It stays in. So that 5 has to stay in. Pair of x's here. 1 comes out. There's no pair for this one. So it stays in. So if you were to simplify the square root of 125 x to the third, simplified, it would be 5x times the square root of 5x. I know we're moving fast here, but I'm going to try and get this all done in a single video here. My board's jumping all over the place. So let's do some of these, pause the videos and give this a try. Unpause the video. So I see this is made up of a 4 and a 3. A 4 is a 2 and a 2, so this gives me 2 root 3. You don't have to do it this way. You could do it in different numbers, but 16 times 3 is 48. This is a perfect square. 4 times 4 is 16. So this is 4 root 3. Same with this. You could do a 5 and a 10. It'll work out the same. Or you could see it as a 25 and a 2. 5 and a 5. This is 5 root 2. Oh, root 2, 12. I got that one twice. X squared will just be x. There's x to the third down here will give you x on the outside and x on the inside. To put it back in, you would square it, add the exponents to get x to the third. Here's some little more complex ones right here. Let's go ahead and do these. 48. This is going to give me a 16 and a 3. So for this 16, 4 comes out. That 3 stays in. This is x squared times an x. 1 comes out. 1 stays in. This is y squared, or y to the square on the outside. Okay, moving right along to rational exponents. It's a lot of material here. You got to do some practice problems. Make sure you work through all the problems in the book. You can write radicals as exponents, and you could go back and forth between the two. So first we looked at exponents, then we looked at radicals, and now we're representing the same thing in either exponents or radicals. So the square root, or the nth root of x, is x to the 1 over the n. And I think of that like if I have the square root of 9, there's no number here, so it has to be a 1. That would be 9 to the first. And this is the square root. So the square root of 9 is the same as 9 to the 1/2, or 3. It could either be a negative 3 or positive 3. Also think of that fraction falling over to the right this way. So x to the m, then I take the nth root of it. Fraction would have to go this way to give me x to the m over n. So if I had something like 8 to the 2/3, this is saying take the cube root, that 3 is that 3, of 8 squared. Well, 8 squared is 64. What's the cube root of 64? Well, 4 times 4, 16. 16 times 4, 64. Okay, let's look at a couple of these examples and practice problems here. So this is saying 27 to the 4/3, which is 27 to the power of 4 over 3, which is 27 to the 4th of the cube root. So I could do this a few different ways. One of the good ways to do this is I'm going to actually stay in fractional notation here. I might recognize 27, 3 times 3, 9, times 3, 27. So I'm going to convert that 27, 3 to the 3rd, right? That's that 27 to the power of 4/3. Well, the multiplication rule, I multiply those together. This is 3 over 1. These 3's cancel, and it gives me 3 to the 4th. 3 times 3, 9, times 3, 27. 27 times 3, 81. My answer is 81. This one right here, simplify this. I have x to the 3rd times x to the 5/3. I've got to use my laws of exponents. So that means I could add across. I have a common denominator, so that's going to give me x to the 6/3. I divide that and get x squared. Pause the video, do these practice problems, and we'll move on. 16 to the 1/2. That is saying the square root of 16. That could be a 4 or a -4. This one right here, I might recognize this as a cube. This is 3 to the 3rd. That's my 27. To the power of 2/3. My 3's cancel. 3 squared is equal to 9. Same thing here. I'm going to cancel this. 5 goes into here once and here twice, giving me x to the 4th. Remember this whole thing right here, 9x squared. That whole thing is to the 1/2 power. 9 to the 1/2, x to the 2 times 1/2. Well, this is saying square root of 9, 3. These cancel to give me x. Okay, let's move this up a little bit here. And then here's a test at the end of exponents and radicals. I'll do some of these, but pause the video and do them yourself, remembering the book has a key in there. Across the top here, I'm going to have a to the 8th, adding x to the 6th, y to the 12th, 1 over z to the 4th. This one's a little tricky down here because that 2 goes to all of them. So that's going to give me 3 squared, 9, a squared, b to the 4th. And then we'll jump down here a little bit. We'll do number 10. This is a hard one here. I do have a common denominator. My bases are the same. I'm going to add across the top to get x to the 4/2 divided by x to the -1. 4/2 is 2 over x to the -1. Now I use the quotient rule to subtract. 2 minus a -1 is a positive 3. Correct answer, x to the 3rd. Okay, there's the answer key if you did them all. And that's going to bring us on to polynomials. So we're still kind of in the advanced algebra topic. You might want to pause the video here, take a little break. We've been doing a lot of stuff. Chapter 10 was multivariable equations, x and y. We solved with either substitution or elimination. But if I have one equation with 2 variables, I cannot solve that unless I have a second equation. From there, we went to square roots and exponents. Square roots and radicals mean the same thing. Exponents say take that number and multiply it by the power that is 2. X to the 5th is saying x times x times x times x times x. Versus the 5th root of x is saying what times itself will give you that square root. So that's going forward and back. Then we looked at rational exponents to make square roots represented with exponents and vice versa. Now we're moving on to polynomials. So a polynomial are different terms set apart by addition or subtraction. The coefficient is a number in front of the variable. The variable will always be the letter a, b, x, y, and the degree of the polynomial will be based on the highest exponent. So this is 3x squared plus 2x minus 5. So this is a second degree polynomial, third degree polynomial. Even though there's no value here, this is a 1, so this is a first degree polynomial. Okay, these come into place a lot with polynomials. The easiest thing here is going to be adding and subtracting first. The only thing that's a little tricky is if it's subtraction, you got to remember to distribute that sign through the whole quantity. So what I want to do here is I just want to combine similar things. So here I have 2x squared plus 1x squared. That's going to give me 3x squared. 3x, oh, excuse me, 3x minus 5x is negative 2x. Negative 4 plus 7 is 3. This is an expression. It can't be solved. There's no equal sign. I can only combine similar things. Example number 2, this is a little harder because I have a subtraction. I'm going to distribute that negative through the whole quantity, giving me the original 5y to the third minus 2y plus 6 minus y to the third minus 4y minus minus makes it positive 2. Combine similar terms, 5y to the third minus y to the third gives me 4 of them. Right, I got 5 of these things minus 1 of these things, leaves me with 4 of those things. Minus 2y minus 4y minus 6y. 6 plus 2 is 8. So I combine all the similar terms. There's another one there. Here's some practice problems. I haven't redrawn these with easier exponents using the equation editor. But what I'm saying here is 6b to the third minus 2b plus 9 minus 3b to the third minus 5b minus minus is plus. Have them all out. Now I need to combine similar terms. I have 6 of these b3s minus 3 of them will give me 3b to the third. Negative 2b minus 5b is negative 7b. Plus 9 plus 4 plus 13. Again, a lot of information. If the previous chapters don't really make sense, it's really hard to do these. All right, now we're going to multiplying polynomials. This is kind of the easier scenario first. A monomial, single term times 2 terms. You got to distribute this through the whole quantity. So 3x times 2x, I multiply the 3 and the 2 to get a 6. X times x. And then 3x times 5 is 15x. It's kind of a classic algebra problem here. I have a mnemonic device for these right here. That mnemonic device is FOIL, F-O-I-L. And that means you multiply the first terms together, the outer terms together, the inner terms together, and the last terms together. There's a lot here. So I'm going to multiply the first terms together, x times x, x squared. The outer terms together, x times negative 3, negative 3x. The inner terms together, 2 times x, 2x. The last terms together, 2 times the negative 3, negative 6. Then I'm going to combine similar terms. I only have 1x squared. Minus 3x plus 2x is minus x, minus 6. And then we have a binomial times a trinomial. Those are pretty hard. You won't really see those in the ASVAB very much. Here's some practice problems. Pause the video and give these a try. Unpause the video. Watch how I do them. 2x times x is 2x squared, negative 8x. Right here, I'm going to FOIL it out. Y squared plus 3y minus 5y minus 15. Combine the similar terms, giving me y squared minus 2y minus 15. It's really a lot here. Now we're going to look at factoring polynomials. Remembering this is kind of our advanced algebra portion of the book. We did that beginning algebra portion first, now the advanced. So the first thing you want to do in a simplification is see if you could factor something out. Well, there's a 3 and a 6, and there's a 3 and a 9. So I could pull that 3 out front. And then there's an x here and an x here, so I'm going to pull a 3x out. Once I pull 3x out of here, I'm left with the 3. Now I'm left with the 2x. Pull 3x out of here, I'm left with the 3. So that's factoring. The reverse was distribution from the previous section. I'm going to check this to see if I did it correctly. The way I check it is I distribute it 3x times 2x is 6x squared. 3x times 3 is 9x. That's originally what I had. Therefore, I did factor it correctly. Okay, give this one a try right here. I'm going to pull a 5 out, a y out, and I think that's the only thing that goes into all of them, leaving me with a 2y squared minus 3y plus 1. The reverse of that would be distribution. That would give me 10y to the third minus 15y squared plus 5y. 1 times 5y is that 5y. Here's some problems here. Some more practice problems. These are kind of tricky. I need to redo these on the editor, but this is saying 4x squared plus 8x. What I'm doing here is I need to pull out that common term. There's a 4 in each one and an x, leaving me with x plus 2. Let me double check that. 4x squared plus 8x. This right here is a special case. Y squared minus 25. This is called a perfect square. Y is squared, and this is 5 squared. And there's a negative. This perfect square factors to be y minus 5, y plus 5. And then the reverse operation is to FOIL it. Y squared minus 5y plus 5y minus 25. Middle terms cancel, and it leaves me with y squared minus 25. That's why it's called a perfect square. You see these a lot in algebra right here. Okay, do number 3. Let me rewrite it first. So on number 3, I have x squared plus 7x plus 10. I'm going to do the reverse of FOILing. I'm going to factor it into 2 quantities. The factors that give you x squared are only an x and an x. Then I'm looking for the factors of 10. When multiplied together, they give me a 10, like a 10 and a 1, or a 5 and a 2, or a 1 and a 10, or a 2 and a 5. That multiplied together, that give me a 10, but added together, give me a 7. So I could see it has to be the 5 and the 2. To give me a positive 10, they either have to both be positive or both negative, but I have a 7 in the middle, so they're both going to have to be positive. Let me make sure I did this correctly here. So my check is FOILing my factoring. First, x times x is x squared. Outer plus 2x. Inner plus 5x. Last plus 10. Combining similar terms. Oh, this was x squared, x times x. X squared plus 7x plus 10. And that is the original one I started with. A lot of information here. There's really be near impossible to get all of this in a short video, but I'm kind of rolling through this book as quickly as I can. Here's factoring polynomials, difference of squares. This one right here, x squared minus 16, is a perfect square. So it's going to be x plus 4, x minus 4. 4y squared minus 9, again, is a perfect square. I'm going to factor it that way. The reverse would be to FOIL it. 4y squared plus 6y minus 6y, middle term drops out, minus 9. Same thing with that, perfect square. 7x minus 8, 7x plus 8. Okay. And then here's factoring trinomials. This is like the one I did previously. This thing right here is called a quadratic, ax squared plus bx plus c. Really common in an advanced algebra course. I am breaking this x squared plus 5x plus 6 down. First way I do this is I look for the factors of x squared, which are going to be an x and an x. the factors of 6 multiplied together to give me a 6, added together to give me a 5. It could be a 6 and a 1. 6 minus 1 will give me 5, but they're all positive or negative. Another set of values would be a 3 and a 2, and then they're both having to be positive. Let's double check that. X squared plus 3x plus 2x is 5x plus 6, so I factored that one correctly. I'll just throw in one more piece here. This is an expression. There is no equal sign. If it did say solve for x, it would have to be an equation. It would have to be set equal to 0. This thing right here would still be set equal to 0. I would factor it so that this would have to equal 0, or this could equal 0, right? It's called the zero-sum property. What times what equals 0? Well, either this is 0 or this is 0, meaning that either x plus 3 could equal 0, 3, or x plus 2 could equal 0. Solving for x here, x could equal negative 3, or subtracting 2 from both sides, x could equal negative 2. So if it's an expression and it asks you to factor it, those are the factors. If it were an equation and you were to set it equal to 0, then you could solve for x, and x would have 2 possible answers. Okay, here's some more practice problems. These are all expressions here. They're hard. Okay, and that takes us to our test on chapter 12. I won't do all of these. Adding, subtracting is going to be a little easier. Pause the video, do the problems, the keys at the end of the chapter. I have 7x squared plus 2x squared. That'll be a 9x squared. My pen's getting tired, which means I must be getting tired. So that gives me 9x squared minus 3x plus 5x is 2x. 2 plus negative 8 is negative 6. Let's do one more here. A squared minus 4a squared. So that's saying I have one of these a squareds minus 4 of these a squareds, or negative 3 of these a squareds. 8a minus negative a minus a negative is positive plus 9a. Negative 5 minus 3, negative 8. Here I have a single term multiplied through the quantity. 4x times 3x squared. It's going to give me 12x to the third. 4x times negative 2x is negative 8x squared plus 4x. So I got to distribute that 4x to the first term, to the second term, to the third term. This one right here I have to FOIL, first, outer, inner, last. Y squared minus 7y plus 2y minus 14, my last term, my first term, my outer term, my inner term, my last term. Combine similar terms. This is going to give me y squared minus 5y minus 14. All right, well, there's the chapter right there. Here's the answer key to it. A lot of stuff. And then we'll move on to quadratic equations from there. All right, if you're still here, congratulations. This is a super long video and only going to get longer. Take a break, walk around, learn how to juggle, something to break up just sitting there studying. And again, the best way to do this is to have paper and pencil out in front of you, take notes. The process of taking notes inside this book really helps get that stuff to stick in your mind, and then do problems before I do them. So pause the video, do the problem. Again, what we're doing right now is we are on part 3, advanced algebra topics, and we're right now on chapter 13. and Chapter 13 is quadratic equations. We're going to work through Chapter 13. There's a test at the end. Go on to functions, and then go on to graphing. There's a lot of same topics covered in all these chapters, and hopefully this longer video will bring them all together. Again, this is all based on this book right here. There are 5 parts, 25 chapters. If you need more help, go back and watch the individual video on that chapter. But what I'm doing now is a series of 5 videos to cover this whole book. All right, with all that said, let's go ahead and jump into quadratics. So a quadratic is a polynomial. It is in the form ax squared plus bx plus c. And then it can be set equal to 0. Just to get an idea of the graph of a quadratic, the quadratic with that ax squared, so if we had something like y equals 2x squared, that's going to, if you don't know how to graph that, you could always set up a t-bar and pick values of x and y. Any value you want for that independent variable, like 0, 1, or 2, or -1, -2. Pick that independent variable, plug it in to the equation. So if I take that 0, plug it in here, 0 squared is 0. 0 times 2 is 0. So the input is 0, the output is 0. 1 squared is 1 times 2 is 2. 2 squared is 4. 4 times 2 is 8. -1 squared becomes +1 times 2 is still 2. So a couple things I noticed. One is if I were to graph some sort of x squared term, it would have the origin in it, 0, 0. From that origin, it would increase, and it would increase at an increasing rate. So over 1 up 2, over 2 up 8, over 3 up a lot more. Any negative value I plugged in would become positive, so it would look like a parabola. So this is really about how to solve quadratic equations, but before we start, I just want to show you what a quadratic will look like. If it's in the form ax squared plus bx plus c, it's still going to be a parabola like that, opening up if it's positive, opening down. We can solve for those points of intersection by setting it equal to 0. So if we say y is equal to 0, where does it intersect the x-axis, or what are the values of x? So just to give you a broader picture of how these quadratic work. So with all that said, let's go back and figure out some ways to solve quadratics. I'll go ahead and close the table of contents here. Okay, so first thing is you want it in that general form and you want to note it. Solving quadratics by factoring is the best case to do it and the most common, especially on the ASVAB, arithmetic reasoning portion. So what you want to do is you want to start by setting that quadratic up in standard form. You want the x squared first, the coefficient in the front, the variable to the highest power, plus a coefficient times x plus just a number is equal to 0. Then you want to factor that quadratic expression. That's going to let us use a zero-sum property, set each one of the factors equal to 0, and then solve for the values of x. I know that's a handful right there, but let me go ahead and do a couple examples here, and it'll start to make sense. So here's my quadratic, ax squared plus bx plus c equal to 0. I've done that. I am going to factor it, which means I'm going to turn it into 2 quantities. Those 2 quantities will be equal to 0. I'm looking at the factors of x squared. Well, they are only an x and an x. The only things multiplied to give you an x squared will be an x and an x. So those have to go in the front. Then the factors of 6 could be a 6 and a 1, a 3 and a 2 and a 3, a 1 and a 6. They need to multiply together to give you a 6, but add together to give you a 5. Both of these could actually work because I could do 6 minus 1 to get 5, 3 plus 2 to get 5. There are no minuses anywhere in here, so that's how I know it has to be this set of factors. So it's a little bit of trial and error. I'm going to try that 3 and the 2. They're both positive. The reverse of factoring is what we said earlier is FOIL. First, x squared, outer, 2x, inner, 3x, which gives me the 5x, last 6. So I factored it correctly. That means either x plus 3 could equal 0, or x plus 2 could equal 0. Subtracting 3 from both sides, x equals negative 3. Subtracting 2 from both sides, x equals negative 2. These are the two possible solutions for x, negative 2, negative 3. If I were to graph that quadratic, it would actually be on the Cartesian coordinate system. It would cross here at negative 2 and negative 3, and it would be a parabola like that. A lot of information here, really built on all of the previous chapters. Okay, let's move on to a little more complex one here, because now I have a coefficient in front of my x squared term. I'm going to factor that. The only factors of 2 are 2 and a 1. Only factors of x squared are an x and an x. Only factors of a 2 are a 2 and a 1, or a 1 and a 2. I need a 5 in the middle. Only way I'm going to get a 5 is by combining these two to give me a 4 and a 1. This is positive. The only way to get a positive is positive times positive, or negative times negative. So either these symbols have to both be negative or both be positive. I'm going to look at my middle term. That middle term is going to tell me how my signs go. To get a negative 5, I would have to do 2x squared minus x minus 4x to give me that negative 5x. So I can see they are both negative. This thing is set equal to 0. This is the zero-sum property, where I'm multiplying things together to get a 0. Either this can equal 0 or this can equal 0, and that's what gives us our two terms. So 2x minus 1 can equal 0. I'm going to add 1 to both sides to get 2x equals 1. Divide both sides by 2 to get x is equal to a half. Over here I have x minus 2 is equal to 0. X minus 2 is equal to 0. Add 2 to both sides. X is equal to 2. My two solutions, 1/2 or 2. Factoring takes a ton of practice. You just got to do a lot of problems. I do have a lot of practice problems in this book, but I should probably put some more in there as well. So again, if you have an x squared thing, a separate x thing, it is a quadratic. You want to put it in general form, ax squared plus bx plus c, set it equal to 0, and factor. If it will not factor, your next option is a quadratic equation. And I know this is a crazy thing up here, and I'll work our way through it. The quadratic equation does not come up that much in the ASVAB. If it does, they will give it to you. This is in case it doesn't factor. So I'm going to go through this pretty quickly. I have my general form, again, which is ax squared plus bx plus c, and it has to be set equal to 0. So this is a 2. When I use that quadratic equation, it is going to give me the answer for x, and it's going to give me two answers. Those two answers are going to come with this plus minus. So I'm just going to say x is equal to, and then what I have here is this is my a value, this is my b value, this is my c value. So we'll take this as an example here. There's no value in front of the x squared. It has to be a 1. So a is equal to 1, b is negative 4, c is 1, and it's set equal to 0. So I'm going to take negative b, negative 4, negative times a negative is positive, plus or minus the square root of that b value, negative 4 squared minus 4, the number 4, times what is in front of the x squared, the a value, 1, times c, 1. That is all divided by 2 times the value in front right there, 1. This is actually going to give me 2 equations here. And I'll write them out here up above. One equation is going to be plus, one's going to be minus. So first I'm going to do the plus. I'm going to have 4 plus the square root of 16 minus 4. 16 minus 4 is 12, all over 2. And then my second equation is going to be minus. It's going to be 4 minus the square root of 12 over 2. No calculator test. These are the correct answers. You can go and simplify them. You got to go back to that chapter on square roots. To simplify 12, 12 is made up of a 4 and a 3. Here's a pair of 2's. 1 comes out. So this is the same thing as 4, that 4, minus 12. Well, 12 is 2 root 3 all over 2. Whole thing's being divided by 2, so I could do 4 divided by 2, which is 2. Negative 2 divided by 2, which is negative 1. So there's my final answer there, incorporating everything I've done in previous chapters. Here, same thing. This is 4 plus 2 root 3. All over 2. This will reduce to give me 2 plus root 3. So that's the quadratic equation. Certainly not easy. The book explains it a little bit more. That thing underneath the square root on that quadratic equation is called a discriminant, right? We had negative b plus or minus b squared minus 4ac all over 2a. That was our quadratic equation. This portion of it here is called the discriminant. If it is positive, then there are going to be 2 solutions. If it is equal, if it is 0, then there will only be 1 solution, because you're going to have this number plus or minus 0 divided by this number, so that'll give you 1 solution. If it is negative, this whole thing is less than 0. If the discriminant is less than 0 and negative, the square root of a negative is a non-real number, so there are no solutions. So you say there are no real solutions or complex solutions. Okay, here's an example, a word problem, projectile motion, getting into physics, and area. I'll just kind of walk through this one right here. Length and width. You have an area of a rectangular garden is 48. The length is 2 feet more than the width. So I'm going to call the width W. I'm going to call the length W plus 2. Converted my sentence into a picture. Convert my picture into an equation. Well, I know area is W, width, times length equal to area. I got to distribute that W through the quantity to get W squared plus 2W equals 48. I recognize it right away as a quadratic. I got to put it in standard form, set equal is 0. So I have W squared plus 2W, subtract 48 from both sides, and that's equal to 0. So there's a lot here. If you kind of get this whole setup, you get a lot of this math. Convert a sentence to a picture, convert a picture to an equation, recognize that equation as a quadratic, put it in standard form, ax squared plus bx plus c, set it equal to 0, try and factor it. Well, the factors of w squared are only going to be a w. Factors of 48 are a 16 and a 3, that won't work. 8 and a 6, that will work to get a 2. 1 has to be positive, 1 has to be negative. This is positive, so the larger one's positive, the smaller one's negative. Quick double check, w squared plus 8w minus 6w gives me the 2w minus 48. Zero sum property, either this equals 0 or this equals 0, which means w is equal to negative 8, or w is equal to 6, right? W plus 8 equals 0. Subtract 8 from both sides. W minus 6 equals 0. Add 6 to both sides. I have two solutions. But we're talking about the width of a garden. Negative 8 doesn't make any sense. So I got to discard this because it doesn't make sense. So my answer is 6. You probably could have done that one through reasoning. But as they get more complex, knowing this whole process is really key. All right, let's move along here. And then here's our test on Chapter 13, quadratics. This is going to turn into an epic video. It's going to be so long. I want to solve these by factoring. So this is x and x. Factors of 10 to give me a 7 will be a 5 and a 2 or a 10 and a 1. Either they're both positive or both negative to give me that 10, positive 10. But this is negative, so it's a negative, negative. This is not asking me to factor. It says solve for factoring. So this thing's set equal to 0. That means x minus 5 has to equal 0. So x is equal to 5. Or x minus 2 equals 0. So I have two solutions, 5 and 2. Make sure you do all of these practice problems in Chapter 13. Solve by quadratic formula. And then here are some word problems. Here's the key right here. Pause the video, work your way through them. I'm not going to do these, otherwise we'll never get done. We're going to move on to Chapter 14 now. And Chapter 14 is functions. At this point right now, I'd highly recommend, if this is all new to you, that you really stop and do a ton of practice. This is really too much for one lesson. If this is all recent review, you had it before, but you forgot a lot of this, you might be able to keep chugging along here. All right, let's roll through Chapter 14. Some of the important vocabulary attached to it. Chapter 14. The input is what you put into the function. The output is what comes out. The input is your domain. Oh, whoops, sorry. Like if I have y equals, you can tell this computer's even tired. Y equals 2x. This is a simple function. The input is saying put something in here. What is the output y? So let's say the input is 3. Input 3 here. The output is 6. 3 times 2. You can see that on a t-bar where I have x and y. I am saying the input is 3. I plug it in here. The output is 6. This is your independent variable, your dependent variable. Y depends on what you put in. If I only want to look at possible values of x, that is called the domain. And if I want to look at the possible values of y, that is called the range. You could think of it as like a vending machine. Your input, your independent variable, is the money you put in. What is the output? The candy bar. Okay, so this is all about function notation. F of x is the way you say it is a function, meaning that there is only one corresponding dependent variable for any given independent variable. But f of x and y are interchangeable. You could say it's a function. F of x represents a dependent variable, y, and it depends on x. That's what that f of x notation means. So before we were looking at if f of x equals 2x plus 1, then f of 3 means 3 is my independent variable. Plug it in here. 3 times 2, 6, plus 1, 7. So it would be an ordered pair, just like we talked about earlier. Ordered pair would be the input, 3. The output would be y, 7. Okay, evaluating functions. So this one right here is saying my function, my model, f of x equals 3x minus 5. Find f of 2. My input is 2. Take that 2, plug it in there. 2 times 3, 6. 6 minus 5, 1. My input is 2. My output is 1. You can see the math is pretty easy. It's really decoding what all this notation means. Here we have a quadratic because it's an x squared, but the notation, everything works the same. My independent variable, x, is negative 1. Take that negative 1, plug it in. Negative 1 squared is 1. 1 plus 4 times negative 1. 1 plus negative 4 is -3. Okay, moving right along here. Here's another one. It doesn't have to be x and y's. And the input might not be a number. It could be a function inside of a function. So if I have h of t, the height of t might be time. What is my height after so many seconds? But my input is t plus 2. I would take that t plus 2 and plug it in for t. So I would say my independent variable, t plus 2, is being plugged in. My dependent variable would be 5 times my input, t plus 2 plus 8. Distribute that 5 through that quantity to get 5t plus 10 plus that 8, right? This is 5t plus 10 here, plus 8. Combine similar terms. My output would be 5t plus 18. A linear function means it is a line, a straight line. The general form for a linear function is y equals mx plus b, where m is slope. Slope is really a gigantic idea in all math because it is the rate of change. Actually, the majority of our math builds towards calculus, and calculus is really the study of slope. So this idea of slope is really important. M is the rate of change, and b is where it crosses the y-intercept. So if I had a graph like this, y equals mx plus b, y equals mx plus b, -2 is my b, 4 is my slope. Slope m is rise over the run. It is always a fraction. So if it's 4, that means 4 over 1. I'm going to graph this on the Cartesian coordinate plane. Horizontal axis is always x. We talked about that. That's really our number line where we started. 0, negatives, positive. In algebra, we're adding a new dimension to it. We're going from 1D, a linear dimension, to area, 2-dimensional, a y-axis. These are coordinates. I could go over 1, 2, 3, 4, 5, 6, 7, whatever. And I could go up however many. Let's say this is 2, right? And then I could go down as well, -1, -2. I could go this way. These would be negative values. Again, Cartesian coordinate plane, independent variable, dependent variable. If I want to graph this, the way I graph this is I start on my y-axis. I look at my y-intercept, my b value. My b value is -2. I put a dot there. From there, I look at my slope. From that point, I rise 4, 1, 2, 3, 4, and I run 1. Any 2 points determine a line. I connect my dots. I put arrows on each end to say it's infinite, and that's how I graph a line in the form y equals mx plus b. Here's another one right here. It has a negative slope. It's -2 over 1. It has a y-intercept of 5. So I start at 5, put a dot there. My slope is I rise -2. Well, how do I rise a negative? That means I go down 2 over 1. Any 2 points determine a line. And there it is right there. This one has a positive slope. I think of that as I write my name in cursive is positive. This is a negative slope going back the other way. Right, so there's our linear functions, graphing linear functions using a table. So I did a little bit of this before. If you don't know how to graph anything, you could always just set up a table, pick whatever independent values you want for x, plug them in. Usually you start at a 0, a couple positives, a couple negatives. You just take these, plug them in. 0 times 3 is 0, -2. 1 times 3, 3 minus 2, 1. 2 is 6. 6 minus 2, 4. And then -1 is -5. -2, -6 minus 2, -8. Have all these values. Certainly don't need that many. These are coordinates. You always want to label this x and y if your pen works. And then I'm going to go over 0, up -2. So there's 1 point. And I could pick any other point, like over 2, up 4. Any 2 points determine a line, connect those dots. And And I could see -1, -5 would be on here. 1, 1 would be on here. 2, 4 is on there. All these points are on here. So this is another way to do the same thing. If you did it as y equals mx plus b, it would have a y-intercept of -2. From there, you would rise 1, 2, 3, run 1, rise 1, 2, 3, run 1, do the exact same thing. But if you don't know how to graph something, set up a t-bar. All right, so that's how to graph linear functions with the t-bar, and then using the slope-intercept form. We've done a fair bit of this. If I have y equals -3, x plus 2, again, that's always a fraction. It's a rise over the run. And my y-intercept is over 0, doesn't go anywhere over, and crosses the y-axis at 2. If I have coordinates, right, if I have 2 coordinates on there, on my Cartesian coordinate plane, whatever they are, whatever they are, like 0, 2, and 1, -1, that means I go over 0, up 2, and I'm over 1, -1, right? Out of those 2 coordinates, I want to find the slope of that line. Well, the slope is going to be rise over the run, where it rises 1, 2, 3 downwards, and it runs 1 positive. So I can find the slope using the equation, any y value minus another y value, over the difference in the x values, x2 minus x1. Y will always be rise, up and down on the y-axis. X will always be run. Okay. And then I know this video is never ending. Few more parts in here, how to find the equation of a line given points. You could do it algebraically, but you could always do it graphically too. Either way. And I think that's going to take us to our test on chapter 4, evaluating and graphing functions, function notation. A lot of pieces here, like I said before. So in this one, I'll just do one of these. I'd pause the video, do the whole test, and then the answers are below. But on this one right here, f of x is saying this is a function. F of x and y are interchangeable. It is equal to 4x plus 7, where this is my slope, this is my y-intercept. It asked me to graph it. So it has a y-intercept of 7. From 7, I rise 4, run 1. So up at 11, I'll be at 1. And I have my 2 points. I connect those points, and it looks like that. There's my graph. If I want to know what f of 3 is, I could find it graphically because it's on that line off my page. Or I could do it algebraically and say 3 goes into there. F of 3 is equal to 3 times 4, 12, plus 7, or 19. So f of 3 up here would be over at 19. So that incorporates how to graph a function and our function notation as well. Here's the whole chapter 14 test. You know, this is a lot. This is a year class, right? We're rolling through it as quick as we can. And then finally, the last chapter in this video, graphing. I have gone over a lot of these ideas in that last section because it ties them all together. But this section, we'll go ahead and go through it and talk a little bit more about graphing. Again, this right here is your y-axis. This is your x-axis. And think of this thing as your number line. Right here is 0. These are negative values. These are positive values. And then this right here is your vertical axis. It's always called y. Always your independent variable, your dependent variable. If I go up 3, I go over. Remember, you walk into a building, you walk over to the elevator, then you go up. So if I go over 2, up 3, that is a coordinate 2, 3. That is my x. That is my y. That is my independent, dependent variable, xy. That is called an ordered pair. These are called quadrants inside of my Cartesian coordinate plane. This is quadrant 1, 2, 3, and 4. The reason why they are numbered that way is in trigonometry, everything's defined as you start here. you rotate counterclockwise, and then you stop. So that's going to kind of put our circle into our coordinate plane, but that is another day. If I have that coordinate right here, 2, 3, and let's say it goes through the origin, any 2 points determine a line. I have that line. The general equation would be y equals mx plus b. General equation is a roadmap to get to your specific equation. Well, I got to figure out the slope of that line. Well, it rises 1, 2, 3. So it rises 3. It runs 1, 2. The y-intercept is 0. So the equation of that line is y equals 3 over 2x plus 0, which you don't have to write in there. Okay, tons of information here. Again, the way to calculate slope is you could do it graphically or algebraically. I kind of glanced over this in the last chapter. If this is a coordinate and this is a second coordinate, I would call this my first coordinate, this my second coordinate. X always comes first, so this would be x sub 1. This would be my x value of my second coordinate. This would be the y value of my first coordinate, the y value of my second coordinate. Slope is rise over run, so I'm going to find the difference in y values. So it is going to be y2 minus y1, or 9 minus 3. Y2 minus y1, 9 minus 3. Then I look at the difference in x values, 4 minus 1. 6 over 3 is 2. That's a slope where I rise 2, run 1. You can see this graphically. It's first quadrant value. I am over 1, up 3. There's my first dot. I am over 4, up 9, 4, 5, 6, 7, 8, 9. What is the slope of that? Well, I rise 6. I run 3. That is a fraction. I rise 6. I run 3. That reduces to 2 over 1. You could also go from this point to this point and do everything. If you call this point 1, that would be fine, but this has to coordinate with that, so that would be x1, y1. Then this would be point 2, x2, y2. And then you would say the slope here is rise, negative 6, over run, negative 3. Same slope, negative divided by negative is positive, 2 over 1. Okay, so that's how you find the slope. Pythagorean theorem is a really important equation. It is, if I have a right triangle, it'll only work in right triangles. It is 1 leg squared plus the other leg squared equals a hypotenuse squared. Okay, this is a great equation to know. If I have a right triangle, and the way I say it's right is I put this little box here to say it's exactly 90 degrees. This is a leg of 3. This is a leg of 4. There are 2 legs in a right triangle. And then a hypotenuse. Hypotenuse is always the longest, always opposite the right angle. I don't know what it is, so I'm going to call it a variable c. Then I have 3 squared plus 4 squared equals c squared. You'll always see Pythagorean theorem on a standardized test. 3 squared is 9. 4 squared is 16 equals c squared. 16 and 9 is 25 equals c squared. I don't want c squared, I want c by itself. Take square root of both sides. Square root and a square, remember from that previous chapter, square root and a square cancel. That gives me c. If I do that to the right side, I got to do it to the left side. c is equal to the square root of 25. 5 times 5 is 25. Actually, negative 5 times negative 5 is 25 as well. So there are 2 solutions, but I discard that negative because I'm talking about the length of a side. So c is equal to 5 using the Pythagorean theorem. That is actually also going to work in the Cartesian coordinate plane too, because if I want to know the distance from this point right here, 1, 1, to this point right here, 4, 3, 4, 5, to this point right here, 4, 5, I could find the slope using that equation, m equals y2 minus y1. But I'm now asking you to find the distance of that blue line. Well, the distance, the length of that blue line is a diagonal, but it will always form a right triangle with a horizontal of x and a vertical of y. I didn't really draw that too well to scale, but 1 to 5 is 4. 1 to 4 is 3. So I could use Pythagorean theorem and get the length of that line, 5. This idea on the Cartesian coordinate plane, horizontal always being your x's, vertical always being your y's, is a gigantic idea used throughout all science, physics, navigation, artillery, trigonometry. Anytime you're looking at angles, it's all going to be based on this. It's actually, if you have a line on the Cartesian coordinate plane, it is considered a vector, meaning it has both direction and magnitude. And why that's so important is when you do an analysis on the way a tank travels, the way a plane, boat, it will always be a vector analysis. It will always be based in the Cartesian coordinate plane. So these are not small ideas. These things have giant ramifications, and it is part of why they are part of any standardized math test. Okay, so we've got the Pythagorean theorem there, which could convert to finding distance between points, finding the point of intersection between two lines. We've actually kind of done this before, but without the graph. Remember, now we have two variables, two equations. We have two ways to solve. One was substitution, and one was linear combinations. So I'll just do one of these. I'm looking at these two lines right here. I think I'm going to combine the two to get a variable to drop out. I'm just going to rewrite that one here, x minus y equals 2. It's called linear combinations. They are lines. I'm combining them. So I combine them, 2x and x is 3x. Y and negative y is 0. 7 and 2 is 9. Divide both sides by 3, and x is equal to 3. That's not my answer. That's only half my answer. Take that answer, plug it back in here to get 2 times 3 plus y equals 7. 6 plus y equals 7. Subtract 6 from both sides, and y is equal to 1. My answer is an ordered pair, an input of x and output of y. Lot of information here. I could do that graphically as well and really tie all this together. I'm just going to do this equation first in red. First thing I want to do is go y equals mx plus b, get it in general form. So I'm going to subtract 2x from both sides to get y equals negative 2x plus 7. All I did here was subtract 2x from both sides to get it in this standard form. This equation right here in blue, I have x minus y equals 2. I think I'm going to bring that y over to the other side to make it positive. That'll give me x equals y plus 2. I want it to look like that, so I'm going to subtract 2 from both sides, giving me y equals x minus 2. There's my second equation in standard mx plus b form. Kind of out of room here. I'll graph over here. Y equals negative 2 with the slope of 1 over 1. So I start at negative 2. And from there, I rise 1, run 1, rise 1, run 1. And I can see I'm going to go through. It's going to look like that. Positive slope of 1, y-intercept of negative 2. Then I have this one right here. It has a y-intercept of 7 way up here, and the slope of negative 2. So I'm going to run negative 2, 1, negative 2, 1, negative 2, 1, and it's going to look like that. Right? Y equals negative 2x plus 7, y-intercept of 7, slope of negative 2, 1, negative 2, 1. It has this point right here of intersection. I could see what it is. I could see on my graph it is 3, 1. Boom. Or I could see right here I solved it algebraically. If you could put all these pieces together, converting sentences to pictures to equations, solving equations, finding points of intersections, and proving it with graphs, you get it. You get the whole point of this whole algebra business in general. And it is a big accomplishment, so pat yourself on the back. If you've endured this whole video to here, you are a student. You are the real deal. I will say that. I don't know if I've ever watched an informative video. Actually, that's been more than 15 minutes. So if you're still here, congratulations. Pause the video. Do this whole test right here. The answers are below. And that's basically a year of algebra just wrapped up. And I don't know how long this video is. It might be 2 hours by the time I'm done editing it all the way down. Any questions, please post them in the comments. I'm trying to do a live class every Wednesday at 4 p.m. West Coast time. The best thing to do is if you got questions, you can just post them in the comments during that live class. I'll have my Chromebook here and then I'll look at it and then try and answer them. All right, well, I appreciate you watching. If you're here, I do commend you for your unbelievable perseverance to make it through this far. So well done and thank you.